All right, hello again. Let's actually work through section 3.3 on inverses now. All right, so to launch in, let's just start off, by computing these two products. So we know how to do that. AB is 1, 2, 3, 4 times minus 2, 1, 3 halves minus a half. And remember, you just do row by column, each time around. And if you do that, you can kind of do it in parallel with me, or instead, you'll get 1, 0, 0, 1. And if you do BA, remember, if you change the order in general, you don't get the same product back. So the products are not commutative. But if you were to do it this time around, row by column, you will still get 1, 0, 0, 1, which kind of acts like a identity matrix in some sense, right? And by that I mean, we actually know what that is. This is I2, and this is I2. Because if you multiply any matrix on either side by this guy in R2, 2 by 2 matrices rather, you'll get that same matrix back. So that acts like the number 1 for us. Okay, so what we'll say here is that a matrix is invertible or non-singular. Those two terms mean exactly the same thing. If you can find some other n by n matrix, B, so that if you multiply A on either side of it, you get the identity matrix with n rows, right? So you get the I with the right number of components. Right, so in some sense, B would be the multiplicative inverse of A, right? So kind of like, and this is not the same, but if you say the multiplicative inverse of 3 is 1/3, because if you multiply 1/3 times 3, you get the number 1, right? But here we don't divide by a matrix, rather we take its inverse, right? So the multiplicative inverse of 3 is really 3 to the negative first exponent, right? Which makes sense, and that's equal to 1. So this is what's parallel here. Typically what we will do instead of writing it as a B, we wanted to note the fact that it has a relationship to A. We'll denote A to the minus 1 as the inverse of A. Okay. All right, and so here, if there is no such matrix, right? So, and we have to find out how you even determine this. But if you determine that there is no such matrix so that you can multiply on both sides of A and get the identity back, then A is non-invertible or singular. All right. So now notice here, you have to be able to do this in either order. And so that implies that if you have a non-square matrix, it cannot be invertible in this sense, because the minute it's non-square, you're not going to be able to commute the two matrices, right? The dimensions will maybe match on one product, but they then can't match on the other because they're different. All right, so keep that in mind, that non-square matrices cannot have inverses for that reason. The dimensions just won't line up to make it work. All right, so I'm going to go to a different page now other than what's in these notes, just to kind of explain something. All right, so let's actually go through, how would I determine that matrix B in the first place, right? I mean, it seems just mysteriously just pop up. How do I do it? So let's just talk theoretically about this. I have our matrix A, and we don't know what the inverse is, so let's call it something. Let's call it a n by n matrix, right? So it's going to have the same number of components as does A, right? That makes sense because you have to be able to multiply A by it on either side. So it has to have the same number of rows and columns as A does. And what we're trying to find, these are our unknowns. We're trying to find those 4 numbers. Okay, so what this means, let's just write it this way. When I write this sentence down, that means that if I multiply these two matrices together, you're going to say, well, yeah, obviously. This is 1, 0, 0, 1. All right. But that really gives me 2 systems, right? In other words, if I multiplied row by column, right, what I should get is 1, 2, 3, 4 times x1, x2 is equal to 1, 0. Right, that's what happens if I wrote my first row by first column, second row by first column. It has to be this guy. And doing the same thing for this, I would get the same sort of system, only now my unknown is y1, y2, and the right side is now 0, 1. Right, so in other words, to find this matrix here, this inverse, I have to solve these two systems. Okay? Now, how do you solve that? Well, if you were you could use back substitution, but I want to get this into a form where I don't have to think, right? So I want to rewrite this in such a way, or so I want to write this as an augmented matrix, same way here. And what I would like to do is perform operations on this, and so that, right, so these are the elementary row operations, right? Typically we say put an echelon form and then just use back substitution, and that's perfectly fine for solving a system. But I'm going to try to get a better sort of more direct way of producing this inverse as a result of operations rather than have to go through a second layer of computation. And so here I'm going to apply the elementary row operations, and so that I can get the identity. So if I can somehow whittle this down so that I get 1, 0, and 0, 1 on this side, then we know here, since the solution of this system is x1, x2, and this would be equivalent to it, then this part here has to be x1, x2. It has no choice in the matter. All right, has no choice. And then here, whatever you get there is that unknown. And same way here, I'm going to whittle this down so that I get the same identity matrix, right? So same thing. The only thing is here, the solution of this system is y1, y2, right? And so the idea, if you were to do these separately, you would be doing the same exact thing, would you not? This matrix is exactly the same in both. So you're going to perform exactly the same operations, just with realizing that when you solve this guy, you get that column. When you solve this guy, you get that column. And so what we do instead, so we don't have to do double work, is we're going to combine the augmented matrices. Right, so I'm going to combine, that matrix is the same in both, right? And this, where my right side's past the bar, right? So I'm using that same matrix on the left, and on the right, I'm using those right-hand sides. Okay? And the idea is to perform the elementary row operations, if you're able to get this down, to the matrix for which this identity, that's I2, is on the left. And then if that's the case, then the columns in this order are on the right. This will be the inverse. Right, so that's the idea here. Okay, all right, so let's actually show that in action. So that is this piece. Here we go. All right, so that's kind of what I was talking about here. Just trying to expand on the reasoning a bit. All right, so we know that the process now to find an inverse, or to go to try to produce the inverse matrix, what we're going to do is put the matrix that we want to invert here and put the corresponding correct sized identity on the right and perform these operations so that we whittle the left-hand part down eventually to the identity, or determine we can't. All right. Once we're there, well, the matrix that occurs on this side has no choice but to be the inverse. Okay. And you know how to do elementary row operations, right? For this guy here, I'm just, to go from here to here, I'm dividing by -2, right? And plugging in, dividing row 2 by -2 and putting that in to row 2. And then I want to put a 0 there. So I'm going to subtract 2 times R2 from R1 and put it into R1. Right, so this guy here is negative 1/2 R2 into R2. This guy is R1 minus 2 R2 into R1. Remember, the goal here was to put a 0 there, right? And so now notice there's your identity. There's that matrix that we started off with. That turns out to be matrix B, right? So indeed, we have succeeded in finding the inverse. All right. Now, so if you have, there are some special cases, obviously. If you go through, and I'm not going to show this, it's actually pretty easy to prove. But if you have a 2x2 matrix, we don't have, there's a formula that you can produce that will show you the matrix every time, right? And so you can go through the elementary row operations if you want to produce it. But in the end, what you'll show is that that will be the right-hand side when you whittle this guy down to the identity. And so this will exist if and only if this restriction holds amongst those entries, right? So, and notice that is product that way minus product that way, right? So as long as that's not 0, the inverse exists because we're dividing by that number, and the inverse form is this guy, right? So as an exercise, just to convince yourself, I would, you should show that A times A inverse is the identity in A2, right? You really ought to do that just to at least convince yourself that it's true, right? I'm not making you go through the actual gory elementary row operations to prove it, but you should at least show that. Okay, so a 2x2 matrix is invertible if and only if that product minus that product is not 0. And we'll give that a name in chapter 5 later on. You might already know what a name is, but for now, just realize that's a restriction for us. All right, so let's go through and determine the inverse using the shortcut. So here, notice all you have to do, the inverse, you switch those guys, right? As long as that's not 0. So let's actually check the restriction each time. This is AD, 4 minus 6 is minus 2, right? So that's what we're dividing by. So it's not 0, so A inverse exists. That's nice. And notice that to get the inverse, if you compare A to this matrix, you're flip-flopping those guys. So you just interchange the diagonal elements. And here, you keep these guys in the same position, but you multiply by a -1, right? And so that's equal to that matrix. And if you were to distribute the -1/2 through, notice what you get is this guy, right? That was our matrix A from the first example. That's exactly our matrix B, or the inverse, right? So it's an illustration, at least, that the shortcut does indeed work. Let's do this one, right? If I want to check out the restriction first, so that doesn't equal that, A inverse equals that. All right. And so here, if I multiply down, -3 minus a -4 is 1. That's not 0. So A inverse exists. It's 1/1 times. Remember what we do. We take these guys and switch them, and then negate those guys. Okay, that's what this theorem tells us, that formula. Okay, just remember that if you're using the formula, to remember which one you switch and which one you negate, right? That's the obvious problem with misremembering here. Okay. Okay, and then here, this one, notice if we check the restriction, you get 6 minus 6, which is 0. Hence, there does not exist an inverse. It's that simple, right? If you were to try to go through the row operations, what you would get is a row of zeros on the left-hand side, right? And so there is no inverse in that case. All right. And so this is a summary. If you were to, we don't have a nice formula like this if you have a 3x3 or beyond, right? There is no nice formula for computing this. So you have to almost rely on this elimination method, right? Reducing this matrix down so that it turns into the identity in the right space. And so here are the steps, right? What we do is we adjoin. So let's actually go through it verbally. Here's our matrix that we want to determine if it's invertible, and if so, compute the inverse. Okay. All right. And so we have that guy. All right, so let's actually go through the row operations. The goal is to do it so that we produce the identity, which is this guy on the left. Okay, so to do that, I want to put zeros in here and here. So let's add R1 plus R2 and plug it into R2 and multiply R1 by R2 and add it to R3 and put that into R3. All right, if we do that, what we get, and we have to do that all the way across, don't forget, all the way across. And so what I get here is 1, 2, 1, 1, 0, 0, 0, 2, 2, 1, 1, 0, 0, negative 1, 0, negative 2, 0, 1. Right, so you just have to go through the arithmetic there to check that out. All right, now what I would like to do is put a, let's see here, a 1 here, right, and a 0 there. So I'm going to do two things at one time. I'm going to multiply R2 by a half and plug it into R2, and then I'm going to multiply R2 by a half, add it to R3, and plug that into R3. Okay. All right. And then I guess I also want to put a 0 there. So why don't we add R1 minus R2 and put that into R1. All right, so let's do all three of those at one time. And if I do that, I get 1, 0, negative 1, 0, negative 1, 0, 0, 1, 1, 1 half, 1 half, 0, 0, 0, 1, minus 3 halves, 1 half, and 1. If that's confusing to do them at one step, just do them separately. That's fine. But they're not, none of them depend on each other, so I can do them all three at once. Okay, and then the next step here, I have got to put zeros here and here. And so the way to do that would be to add R1 plus R3 and put it into R1, and then subtract R2 minus R3 and put that into R2. Okay, and if I do that, lo and behold, I do get the identity on the left, and on the right, I get minus 3 halves, minus 3 halves, I think, or minus 1 half, pardon me, can't read my own writing. 1, 2, 0, negative 1, and minus 3 halves, 1 half, and 1. Okay, so A is invertible, and this is the matrix. So it's certainly tedious, but certainly doable. It's all on elementary row operations to get the inverse. Okay. All right, now let's try this guy. What happens in this particular case? Oops. Increase. Let's do that. All right, so let's do the same thing. I'm going to adjoin. There we go. Here's 1, 2, 3, 0, 1, 1, 1, 4, 5. I'm going to adjoin the identity operator or identity matrix to that side. And I'm going to try to put in or try to get the identity over here. So first thing, I want to get rid of that. So I'll put a 0. So I'm going to subtract R3 minus R1 and put that into R3. If I do that, the first row doesn't change. The second row doesn't change. And the third row becomes this guy. You can check me on that. Okay. And now I want to, eventually I wanted to get a 0 here because I want eventually 1 there. So to do that, I'm going to subtract 2R2 from R3, right? So multiply this guy by 2, -2, and add it to R3 and replace R3 by it. The minute I do that, the first 2 rows don't change, but the bottom row, I get a 0, 0, 0, -1, -2, 1. And now the problem is there's no way on earth I'm going to get this into the identity matrix, right? There's a row of zeros. And the minute there's a row of zeros, if you remember our thing before, A is not invertible, right? There's no way you're going to get an inverse in this case. All right, so that's all it takes to show that if you're going through these row operations, if you can produce a row of zeros on the left-hand side, there's not going to be an inverse. Okay, so now why do we even want an inverse, right? So we know that systems of this form arise, right? So we know that we'd like to solve these guys. And so if there is an inverse, if A has an inverse, I know that I can multiply both sides by it. And we'll get to these properties in a minute. And we know that by how you multiply matrices, I know that these are the same on the left. Okay, but if those are the same, we know that's the identity matrix. And identity times any vector is the vector. And so, at least from a theoretical standpoint, I can solve those systems using the inverse of A if it happens to exist. And that's only one, right? There's only one inverse of A if it exists, and B is fixed. So this would be a unique matrix, which argues that this would have a unique solution, right? Computationally, of course, trying to find the inverse is laborious. We just saw that with a 3x3 system. Imagine having a system of 50 equations and 50 unknowns, and yep, we know the inverse exists, but finding it is an absolute nightmare, right? But at least in theoretical arguments that you'll see, even in differential equations or whatnot, knowing the existence of an inverse can help you prove a theorem, and then there are other ways computationally to get at the solution. Okay, so let's actually try to solve this using the inverse matrix, right, if we can. So let's first write it in matrix form. Remember, to do that, we pluck off the coefficients here, right? They're already in the right order, right? So the coefficient matrix is 1, 2, 1, -1, 0, 1, 2, 3, 2. And I multiply that by the unknown, right? That produces the left-hand side. And then we set that equal to 2, 4, 3. The minute we do that, from the previous problem, we know this was the A from example 3A, right? So A inverse exists, and so the solution here, let's call this A, is equal to A inverse times 2, 4, 3, and I know what A inverse is from the previous problem. I'll just write it here. It's -3/2, -1/2, 1, 2, 0, -1, -3/2, 1/2, 1, and then that's times 2, 4, 3. Okay. And then you can compute this, right? Row by column, row by column, row by column. You can actually compute that. And if you do, in the end, you could check me on this, you get the vector -2, 1, and 2. All right, so just another way of finding the actual solution, especially if you have the inverse in hand. Okay, so now we can actually go through and add in more conditions to that unifying theorem that we had. Namely, we already know the equivalence amongst these guys. Okay, and we also know that A is invertible if and only if the columns span Rn, because there can't be a row of zeros in that case. And so this guy is equivalent here, and 1 is also equivalent to 4. Right? So we just argued those two, but we knew the 2, 3, and 5 were already equivalent. So the minute 1's equivalent to 3 and 1's equivalent to 4, they're all 5 of them are equivalent. Right? So all of these have logically are equivalent. Okay. Next up are our cancellation laws. So remember when we have this sort of thing from just algebra, if you had 3x equals 3y, then we knew we could divide both sides by 3 to get x equals y. And that was because 3 was not 0, right? 3 had a multiplicative inverse. It was 3 to the minus 1. Well, same thing here. If the a happens to be on the same side, right here, this is kind of important because in R, if you were just dealing with real numbers, 3y and y times 3 meant the same thing, right? Multiplication was commutative there. And so it didn't matter what side the 3 was on, you could cancel it out with a 3 in the bottom. Here, that's not true, right? So we know that AB and BA are not the same necessarily. And so here, you have to be able to apply A inverse to the same side to be able to get rid of it, right? So if A is invertible, if we know this to be true, if AB is equal to AC, then I can apply AB to both sides. I know that matrices are associative, right? So I can do that, assuming that all products are defined, which they are. And that's the identity each time around. Right, and so you get B equals C rather. Same way on the right, if I just apply A inverse on the right side, then all you're going to do is switch the A inverse A to an AA inverse, right? So for this guy, I'm going to multiply on the right side by A inverse, regroup, but those are also the identity, and so B is equal to C again, right? So that's all fine as long as A is on the same side. If that's on the opposite side, you can't say the same thing. All right, so that's something called cross cancellation, right? So if I have this, if I have AB equals CA, I cannot just cancel the A's and get B equal to C, right? And so here, just keep that in mind. If A is on the same side, you're in good shape for canceling it. All right. Rather than prove all these, what I'd like you to do is just go through perhaps and check them for a couple special cases for which you can compute the inverse, right? So maybe a 2 by 2, since we have the formula, just go through and compute there just to convince yourself that these are true. But some of them are intuitive, right? So A inverse inverse, if you invert something and then invert it back, you should get back the original. And so that is true, right? If I take the inverse of an inverse, I should get back A. And that's like saying, it kind of behaves like the exponent rules, I dare say, right? 3 to the minus 1, all to the minus 1, you would have multiplied the exponents to get the 1 back. So that emulates that result. Similarly here, A to the K, if I take the inverse of a power, it's like computing the power of the inverse. And so you can interchange those two. Again, by exponent rules, that is easy to see, but that's not what's going on here because the A is a matrix. So that actually takes some doing by induction to prove. Right. So, but again, just verify that for a couple of examples just to make sure you see that in fact it holds. If I want to invert a constant times a matrix, then as you might expect, you invert the matrix and multiply by the reciprocal of the constant as long as C is not 0. Right. So remember, C can't be 0 here. She can't divide by 0. Right. And then same way, if I invert a transpose, it's like saying, let's transpose the inverse. Right. And then this one is kind of bizarre, but it works. It actually comes up with functions a lot, with inverting a composition of functions. And it's based there on the order in which it requires you to unpeel them, right? So let's actually show this one. If I wanted AB inverse, so let's prove it on the left side. What this matrix, if it exists, is unique, right? And so the only way I'm going to get that matrix to be into I is if I kill off A and B separately. So to kill A, I have to have first an A inverse, right? And then once they're gone, I have to kill B with a B inverse, right? So what that suggests is that a candidate for the inverse should be this guy, but in the reverse order. So invert B and invert A, but in the opposite order. And that's true, right? Because you can regroup, right? So I can group those guys together to get then that product. We know that product is I. And so that's in a nutshell why that works, right? It's the order reverses when you have to undo a product or a composition. Okay. All right. So, and here, like I say, you can kind of generalize things if you want. This is just more of an FYI. You'll be asked to tinker around with them in the homeworks, but it's not necessarily something you want to memorize, but nevertheless. All right, let's link this now to our linear transformations. Remember, a linear transformation is completely determined by a matrix A. And so what if I want to find the inverse of a linear transformation, right? An inverse, T inverse of X, when applied to T of X, should give you X, right? So as an operator, as a mapping, it's something that when you plug this in as an input, you get X back, right? So in order for this to happen, right, we know that T of X is equal to AX by definition, but the only way to get X out is to apply A inverse on the left side, right? And so what that suggests is that the inverse operator is A inverse of X, right? So in other words, to invert a linear transformation, you basically invert the matrix A used to define it, right? So T is invertible if and only if the matrix A is invertible. But the only way T is invertible is if it's one-to-one and onto for those reasons that are linked back to A, right? A has to span Rn and it has to be comprised of linearly independent vectors. So given those equivalences, the only way any inverse exists is if all of these guys hold, right? So we're kind of building up that sort of repertoire in our unifying theorem. It all goes back to that sort of the pivots, as it turns out. It boils down to the existence or non-existence of the pivots in rows and columns. Okie doke. So here, this is just, I'll leave this to you just kind of as a fun sort of thing, but you can try off example 5, right? This comes up in coding theory, cryptography. So if you're interested in that sort of thing, this is just a little fun application of linear transformations. Okay, very good. So that's the end of 3.3. Go ahead and try the problems. They're not that bad. Again, it'll give you kind of a good review of all of our theorems and techniques with matrices. So kind of take your time through it and let me know if you have any questions. All right, take it easy.